Okay, in this video we're going to look at the general description for the position time graph of an object that's oscillating. So a simple harmonic motion. Now what we've seen from the lab is that the position of an oscillator undergoes a sinusoidal curve. And more specifically, in an object like the mass spring oscillator, if I displace it to some amplitude A, some x position called A, and let it go, it'll oscillate back and forth from A to minus A. And if I plot that versus time, I get this cosine curve. So let's try to understand this expression and develop a general expression that'll work for all position functions of an oscillator. So this is my general format for a cosine graph. X of t equals A cosine of bt. Now this A is related to the amplitude, or the height of the cosine graph, while b is related to its period. So I see that a couple things. One, I can see that this term is A, my maximum amplitude, which is x max, because at t equals 0, right, I have x of t equals A cosine of b times t. It doesn't matter what b is. Cosine of 0, if I start at 0 degrees or 0 radians, either way, is 1. Okay, so when I'm at a time 0, I'm at my maximum amplitude, so the x max is A. So that's pretty easy to see. Now, the relationship for B, what B is a little harder. So let's think about my oscillator in terms of circular motion and a unit circle. So if we think of a unit circle, if we start at a 0 radians, as we rotate and go to pi over 2 radians, pi radians, 3 pi over 2 radians, all the way to 2 radians, the cosine function changes. So at pi over 2, the cosine is 0. At pi, the cosine is negative 1. At 3 pi over 2, the cosine again is 0. And then back to 2 pi, if I've completed one revolution, I'm back to a cosine of 1. So the cosine function changes as I go around through a full cycle. Well, we also know that the period of one revolution is the time it takes to complete a 2 pi cycle. So I can relate the period of my cosine graph to the period of a circle. So how does that help? Well, I see that in my simple harmonic motion, I come back to the same place I started every t seconds, so every full period. So whatever my value is at time 0, I must also have the same value at time t. So when I evaluate x of t at t0, I get A, or x of 0 is A, my maximum amplitude. Now, x at my period, whatever that is, must also be A, because I've completed the circle, I've gone down one full cycle and back, I have to be at the same position, that maximum position. So what that tells me is that the cosine, okay, so for me to be back at amplitude of A at time t, then the cosine of that function, whatever it is, of that expression, has to be equal to 1, right? So when this is 1 again, then I will be back at an amplitude of A. So when else does the cosine of bt equal 1? Well, it's when I've completed a full cycle. So when I've gone 2 pi revolutions, right? So what I have to prove here is that when b times t equals 2 pi, then I will have completed one revolution. I will have completed one cycle. I will be back to an amplitude of A. So now at t, right, b times my period equals 2 pi. So b has to equal 2 pi over t. All right, so this helps me to see my general expression for the position as a function of time for a simple oscillator. X at t equals A, which is my maximum amplitude, times the cosine of 2 pi over t times the time. Let's check it to make sure it works, okay? So at time t over 2, it looks like I'm at my minus A amplitude. So when I evaluate this, let's do this. I'm running out of some space. Let's see. So x at t over 2 equals A cosine of 2 pi over t times t over 2. So that equals 2's cancel A cosine of pi. Well, the cosine of pi is minus 1. So I'm at minus A. So good, that checks. I should also be able to evaluate it here. At a quarter the period, I should be when I cross my 0. So x at a quarter of the period equals A cosine 2 pi over t times t over 4. So that's equal to cosine A cosine of pi over 2. Well, I know the cosine of pi over 2 is 0. So I get 0. All right, so it checks out. The other way that we will write this, so this is our general expression for x as a function of time. Since t is 1 over f, oftentimes instead of writing this as 2 pi over t, you'll see this written as, draw this up here, sorry about not creating good space, x of t equals A cosine of 2 pi times the frequency times t. So there is your general expression for the position of an oscillator as a function of time. And that's it.